Okay. We'll continue to discuss, potential flows. Um, First of all, um, we assume flow is incompressible. Incompressible, because we are interested in water. Okay. Inviscid, because high Reynolds number. Since we have a high Reynolds number, so we can assume the flow is inviscid, although the Reynolds number is not infinite, but the viscosity effect is confined in the very thin layer around the body. And then since the motion starts from rest and we neglect viscosity, we can assume the flow is in rotation. And the irrotational flows, which we call potential flows. As we discussed last time, we can represent velocity field by gradient of velocity potential. That's why we call potential flows. So since we assume vorticity is equal to 0, by definition, curl of velocity vector is equal to 0. That's what the vorticity is. And from here, we know mathematically if velocity vector is gradient of scalar function, then this velocity vector satisfies this condition. Okay, so this is a vector identity, and this phi is in general a function of x and x, y, z, and t. So this is a velocity potential. So this is a rotational condition of irrotationality, and then from incompressibility, so this is a irrotationality, and incompressibility which is divergence, U has to be divergence free, and this gives you the equation for velocity potential phi, and that will give you this. Okay, so that's why we have a Laplace equation for phi. Actually, I said irrotationality, but also this is true because we neglect viscosity. Okay, so irrotationality can be guaranteed only when you neglect viscosity. Okay, so once you solve this Laplace equation for a known phi, then you can find velocity field by taking gradient, and the only physical variable that we don't know yet is pressure. Okay, so the pressure can be obtained from Bernoulli equation that you have seen, but let me derive quickly. So since we neglect the viscosity, we start with the Euler equations. Which are the Navier-Stokes equation with the zero viscosity. So that end up with this. Okay, and then P, and this omega, capital omega, is the gravity term. So omega is minus gz. So z is vertically upward. So when you take a gradient of that, so xy component is 0, and you only have a z component which is minus g. So since u, vector u, is written in terms of velocity potential, we just substitute here. Okay, so this is a u, and then we have gradient of phi, dot gradient, and gradient phi. So I just replace vector u by gradient of phi. Oh, sorry, I forgot gradient here. And then we assume the density is constant. So we have P over O here. I can pull inside. And then we have a gradient of omega. So this gradient and time derivative linear operators. So I can replace the order of, I can switch the order of operation. So I can rewrite this, for example, gradient of d phi dt. Okay, so which is same as that. And then I can pull, all the gradient to rewrite that as this. So the first term gives me d phi dt, and the second term gives me 1/2 velocity squared. And then when I move, the right-hand side to the left-hand side, I end up with P over rho. And then I have a minus omega, which is gz. Okay. So what I did is I just pull out this gradient. Here, this guy is nothing but del divided by 2, which is what I wrote here, over there. So I pull out all the gradient, and then you end up with this. So this is nothing but the Euler equations written in terms of velocity potential. So what this equation says is this term inside of this square bracket is independent of x, independent of y, and independent of z. So d dx is equal to 0, d dy of this guy is 0, d z of this guy is 0. So this term, the expression has to be independent of x, y, and z, which means, this implies d phi dt plus 1/2 plus P over rho plus gz has to be some function of time. Although I don't know what that function is at this point. Okay. So this is only a function of time. When I take the spatial gradient, that gradient is identically 0. So this is a Bernoulli equation. Actually, Bernoulli equation has different forms depending on what your assumptions. And here, these are the Bernoulli equation for unsteady irrotational flow. Okay, unsteadiness is here. For steady flows, right, which means nothing depends on time, then this expression can be written in this way. Some constant. But otherwise, if it is unsteady, then you have to use this. So the step is solving an Laplace equation first with the appropriate boundary conditions. Whenever you have a boundary in your domain, you have to impose boundary conditions. And then once you find phi, then you can find the velocity field in this way by taking gradient. And also you can find pressure from here. Okay. And then since you find pressure from Bernoulli equation, and then the hydrodynamic force, as we saw before. So this is body surface. So hydrodynamic force exerting on a body is given by this. So you find this, and then you just integrate after you multiply pressure by normal vector, and then you'll get a hydrodynamic force. Okay. So that's what we are going to do. Okay, today we are going to solve Laplace equation, and then we'll find pressure, and then we'll integrate that pressure to get the force acting on a body. Okay, any questions? All right. Then we'll look at the first problem, which is the most fundamental problem and the simplest the problem is the circular cylinder in a uniform flow. So we are looking at two-dimensional problem because circular cylinder is like this. So you look at the cross section, flow is going this way. So this is circular cylinder, okay, infinity long, and flow is going this way, and you're looking at cross section, and since this cylinder is so long, the variation along this transverse direction is negligible. Okay, so you're looking at only this cross section. So if I draw that cross section, I have a circular cylinder, flow is coming here. And let's say the speed of flow is u, and which is constant. And the radius of a circular cylinder is let's call r. Okay. So here we want to know how the flow changes as the flow passes this circular cylinder, and we want to know velocity field and pressure and hydrodynamic force. So we are looking at the steady flow. This is independent of time, and then we assume the flow started a long time ago, and we let the flow pass this circular for a long time. Then nothing will change in time, and therefore the velocity, what we are looking at is velocity potential that depends on only x and y. Okay, so this is x and this is y. So let's put the origin here, at the center of circular cylinder, and then we are looking at the velocity potential as a function of x and y. This circular cylinder can move in this way with a constant speed, but this one is exactly this. So first of all, if you solve this problem, then this problem is unsteady, time dependent, because the position of circular cylinder keeps changing, okay, as it moves. So if you look at the flow field changes in time continuously. At t equal to 0, this cylinder was here, and sometime later you will see a circular cylinder here. So the flow changes in time. But if you're sitting on this circular cylinder, at the center of circular cylinder, then to you, the circular cylinder is stationary because the circular cylinder is moving with you, and then to you, there's since this guy is not moving, and it looks like flow is coming toward you. Okay, so this is a change of reference frame. So this is if you use in a moving frame, in a frame of reference which is moving with the circular cylinder, then this problem, or the original problem of this, is exactly this. Okay, the reason why we do this is we neglect time dependency. So when we use a different frame of reference, then the problem is steady, time independent. Okay. But the solution is almost identical, but we'll talk about that later. But at this moment, we assume circular cylinder is stationary, and the flow is coming toward circular cylinder, and then we solve the Laplace equation. So the governing equation is the Laplace equation, as I said. You can solve Laplace equation in many different coordinate systems, and this time it's easier for us to use polar coordinates or cylindrical coordinates because the body geometry is a circle. If geometry is different from circle, for example ellipse, then you can use elliptical coordinates. But since you have a circular cylinder, you can use cylindrical coordinates or polar coordinates in this for 2D, and then the Laplace equation can be written in the following way in the polar coordinates. Okay, so here R this is R radius, and this angle is theta. Okay. So instead of using x and y, we use R and theta. Yeah. In polar coordinates. The reason why we use the polar coordinate is obvious. We can easily represent body when we use polar coordinates. Here, body surface is located at R equal to capital R. That's it, right? So this body surface is located at R is capital R, which is constant. But if you use Cartesian coordinates, there's no way to represent body surface that easy. Of course you can do that. Why is since you have this, and you can write y in terms of x and so on, but it's still complicated than this. That's why we use the polar coordinates in this problem. Then we solve this Laplace equation by using we can solve using a different method to solve Laplace equation, but here we are going to use the separation of variables. Okay, that's the the easiest the method to solve, and therefore we can write velocity potential phi as a function of, can I change this to A? Sorry. Then I can use capital R here, unknown function for function for in R. So phi is a function of R and theta this time, okay, instead of function of x and y. And we assume the function is separable, meaning that you can write the solution in terms of product of two functions, and each function depends on each coordinate. Okay. So if you want to use the xy coordinate, and then you might want to do something like this for separable solution. But for this problem, if you use the Cartesian coordinate, this wouldn't work. Okay, you cannot find the solution by using separation of variables in Cartesian coordinates, because the body the surface, the representation of body surface is complicated. But since if you use a polar coordinates, then it's easy, because body surface is nothing but r equal to a. So basically, for this problem, we use polar coordinates. We adopt polar coordinates to use separation of variable. So that's what we are trying to do at this moment. Okay. All right. The other thing that I want to point out is this Laplace equation is linear, as you can see. So this is the only unknown. There's no product between different unknowns. So the solution, the general solution, can be represented by linear superposition of all possible solutions. Okay, that's a beauty of linearity. And if you find so since the Laplace equation is linear, the solution, general solution, can be represented by a linear superposition of all possible solutions. Okay? So meaning that the velocity potential phi can be written as phi uniform flow plus that the effect of body in a uniform flow. So suppose there is no body inside, then we can neglect this guy, and that's it. Since we have a body in the flow, we need an extra term like that. Okay. So if this is a solution, and if this is a solution, then I can do the linear superposition to write the general solution. That's what I said here. So once again, this is a velocity potential because we have a uniform flow, and this capital phi is due to the presence of we need this guy because we have a circular cylinder in the domain. So if you don't have a circular cylinder, that's it. First of all, uniform flow, velocity potential for uniform flow can be easily found. So when I take a gradient, I have to get u. Okay, and also direction is x direction. So what do we need? We need u times x. Okay? So when I take a x derivative, I'll get, so if I take a uniform flow, then I'll get u and 0 in Cartesian coordinates. And since we're using the polar coordinates, this is nothing but r cosine theta. Okay. So x is r cosine theta, y is r times sine theta. So x is r cosine theta. So this is a uniform flow, the velocity potential for uniform flow. And the question is, what is that? Phi. Okay? Also, as you can see here, uniform flow, the velocity potential uniform flow is a separable form, some function of r times some function of theta. Okay? So that's why we can use the method of separation of variable. Now, so now we are solving the Laplace equation, and then we have to impose boundary condition. We have boundary here, and also we have boundary at infinity, although we don't see it. Okay, it's an unbounded problem for the time being. Or later, we might have free surface here, but at this point, we neglect free surface. There is no free surface, and this circular cylinder is submerged. So we don't see free surface over bottom. If it is an unbounded problem, then we have a imposed boundary condition at infinity. Okay. So boundary conditions that we have to impose is first of all we have to impose boundary condition at the body surface. On the body surface. So on body surface, the boundary condition is given by d phi dn equal to 0. In other words, normal velocity on the body surface has to be 0. Flow particle can move around the body, so tangential velocity doesn't have to be 0. If it is a viscous flow, as we know, due to the no slip boundary condition, this guy has to be 0. Tangential velocity has to be 0, right? But in viscous problem, particle can move around, but the normal velocity it has to be 0, or this way or the other way. Fluid particles cannot penetrate into the inner body. Therefore, normal velocity. So the normal velocity has to be 0. Okay. Mathematically, that can be represented by gradient of phi dot n. Okay. So this is a normal velocity is equal to 0. That's what boundary condition, the boundary condition that you have to use. Shorthand notation for this is, so I often write this way, but what I mean by this is this. Okay? So this is a shorthand notation for this guy. Just in case that you haven't seen this, you're just taking inner product between velocity vector and the normal vector. That's how you get the velocity component in the normal direction. Just like, if you want to find the x component, what you do is the unit vector in the x direction, then you will get d phi dx. Okay? If you want to find the y component, then what you need to do is take the inner product between these two, and then you will get a y component. Like that, if you want to find the normal component, then you have to do this. Of course, if you want to find the tangential component, then gradient phi dot the unit vector in the tangential direction. Okay, that's how you do it. So this time, since we are interested in normal velocity, we take the inner product between velocity vector and normal vector. Also, although we don't see it, at infinity, the velocity has to be bounded. Yeah. Meaning that cannot be infinite. Okay? So we have to impose, these two boundary conditions, and then we can find the solution. You might wonder why you need only two boundary conditions. Okay? Or why can't I use only one boundary condition instead of two? Why do I need two? The answer is, the Laplace equations are second order differential equation. You have a second order derivative. Okay? Phi xx or phi yy. So you have to integrate twice to get something. Whenever you integrate once, you end up with the integration constant, right? So you are integrating twice, so you end up with the two integration constants to determine those integration constants can be determined from two boundary conditions. Okay. All right. Then let's look at boundary condition for capital phi. So we know this guy because we have the uniform flow is given to us. So we know what this guy is as we wrote here. And what we really need to do is find this. Okay? So let's formulate the problem for capital phi. So problem for capital phi. So this is called the boundary value problem. Boundary value problem for phi, because we find the phi by imposing boundary conditions. Okay, that's why we call boundary value problem. So we start from here, Laplace equation, and now does this guy satisfy Laplace equation? Of course, yeah. If I take a second derivative of that, this is 0. Phi xx plus phi yy doesn't depend on y, so I don't have to worry about second derivative with respect to y. But when you take a x derivative, second derivative of x, that is 0. So this is the solution of Laplace equation. And so uniform flow plus capital phi is equal to 0, meaning that this guy is 0, and we end up with this. Okay. So once again, we have to solve Laplace equation for capital phi. And now we have to write the boundary conditions. So I said that d phi dn is equal to 0. And now I put what I had before. So this one is capital D phi dn is equal to minus d phi uniform flow dn. Okay? Because phi is this plus this. then I move to the right-hand side. The right-hand side is minus gradient phi. Let me put u. It's just efficiency in a uniform flow. Dot n. Okay? And then we know this is only u component in the x direction. So all I need is the x component of a normal vector, because this is u and 0 dot nx component and y component. Right? So in that case, what I need is u times nx. Nx is x component. So finally, what we end up with is d by dn is minus u and x. On body surface. And the last boundary condition that we have to impose is this. So when I take a gradient of velocity vector, then I end up with, right, this guy, plus this is bounded, because this is u and 0. X component is u, and y component is 0, because this is uniform flow part. This part, I say absolute value of gradient of phi goes to 0 as on S infinity. Okay. I said, velocity has to be bounded. I didn't say velocity has to vanish over here. But here I said, this velocity, vanishes at infinity. The reason why I'm saying is there is a circular cylinder here. Flow is coming. If you are far away from this circular cylinder, then the effect of circular cylinder will be present near the circular cylinder. But if you're far away, then I wouldn't see any perturbation due to the circular cylinder. Okay, so I will see the uniform flow again. Far upstream and far downstream, I only see uniform flow. Near the circular cylinder, I would see some effect of circular cylinder. But if you're far away from the circular cylinder, then I will see only uniform flow. That's why I said this perturbation. This is a uniform flow part, and this part has to vanish. Okay. And also, this condition is consistent with this, because total velocity vector is bounded. Okay, so those are the boundary value problem that we have to solve. So once again, approximation plus two boundary conditions. Is it clear? So unbounded problem, the formulation is almost the same. Okay? Whatever the geometry, you have to end up with this. Here, I didn't specify what kind of body you have. This has to be, this boundary value problem can be applicable to a body of arbitrary geometry. So far. Okay. As long as you have a uniform flow. So this is a boundary value problem for phi, okay? And let's solve this problem, this boundary value problem for this particular, geometry. And but before we do that, let me look at the body boundary condition again. For that geometry, body boundary condition. So d phi dn has to be minus u and x. Okay. So here, normal vector has to be away from fluid. So this is normal vector. So in other words, normal vector is in this way. So what is the normal vector in polar coordinates? I need a two component, x and y component. So this is my normal vector. So I need x component and y component. So this angle is theta. So this angle is theta. So what is a x component? So this is theta. So this part is nx, which is the length of normal vector is 1. Okay. So 1 times this angle cosine theta. Okay. And so x component is minus cosine theta because the direction is a negative x direction. And also y component has to be sine theta with a negative sign. This is not true for any geometry. Now, from now on, we are only talking about the circular cylinder. Okay, and therefore, we can rewrite the right-hand side by using the representation of a normal vector. Also, in addition to that, ddn can be written in terms of ddr, r derivative, because d phi dn is nothing but minus d phi dr. So r direction is outward and normal direction is this way. So d phi dn can be written in this way. And then we combine all this, we end up with d phi dr with a negative here sign, and then u and x. Okay. And on body surface, which means at r equal to, for this circular cylinder, at A. So this is a boundary condition that you have to impose. So from here, we have some hint of what kind of a function we need. So phi, as I said, we are using separation of variables like this, right? And now you're taking r derivative, that x only here, and then function of theta is equal to minus u cosine theta. And you evaluate only r equal to A. So you can imagine what h theta is. What is it? So I'm going to write this. I'm taking derivative. And then r, instead of r, I have to evaluate at A. So taking r derivative, so this is constant now because I evaluated A. And then theta dependence only here and here. So h theta is cosine theta for this particular problem. Okay? So we can write phi as function of r times cosine theta. Because, the boundary condition says, this guy has to be constant. And then theta dependence appears here and here. Suppose that my HF theta is a sine theta, then there is no way to make, this condition be satisfied. Because sine theta, cosine theta, they cannot cancel out. Okay? So therefore, this capital phi has to be this form. The only question is, what is the capital R that R dependent? How do we get that? We substitute in the Laplace equation. So we start from the Laplace equation in polar coordinate. Right? Then substitute, in here. Then I have R double prime, R, and cosine theta. That prime means, derivative. And then 1 over R prime, cosine theta. And 1 over R squared here. And take the second derivative, which is R times minus cosine theta. Because if you take a first derivative, cosine becomes minus sine, and then when you take a second derivative, sine becomes cosine. So I can drop cosine theta, and therefore I end up with the following ordinary differential equation with a negative sign. Or you can multiply R squared okay. So this is ODE, ordinary differential equation. And this particular form, when you have R squared with the second derivative and R times first derivative and R, then you can find the solution in this way. We assume R is R to some power of M, and then you can find the M when you substitute into here. Okay, that's because of this particular form, you have to use this. I don't know whether you remember this or not, but I'm pretty sure that you learned this, when you took a applied math course as a sophomore student. But anyway, so plug in here, and then R squared. When I take a second derivative of this guy, which gives me M times M minus 1 and R M minus 2. Okay, so that's the second derivative of this guy. When I take a first derivative, I have, right? And then I'm taking another derivative, then I'll get this. Okay? So that's what I wrote here, then multiplied by R squared. And then I have plus R and first derivative, and then minus R to the M is equal to 0. Then as you can see, this times this is R to the mth power. this time this is r to the mth power, and this is r to the mth power, and then you can drop, and then you end up with m minus 1 plus m minus 1 is equal to 0. And then this one is m squared minus 1 equal to 0. So now you can see why we can do this, because all these are all these terms have the same power. So m is either plus 1 or minus 1. So finally, we found the expression for velocity potential phi, which is r times cosine theta, and the capital R is nothing but this. So one is r, m is 1, so I don't have to write it, plus the other is minus 1, so which is 1 over r. Okay? But I need it has to be linear combination because it's a linear problem. These are the possible solutions. 1 over r and r are possible solutions, and I have to take a linear combination. So I can say a r divided by r plus b divided by r. So these are the linear combination of all possible solutions that I said here. At this point, I don't know what capital A and capital B are, which are constant, times cosine theta. So that's what we found by solving Laplace equation. So as I said, I end up with the two unknowns because I integrate twice. So as you can see, I have A and B. Now I'm going to find the A and B by imposing two boundary conditions. One this, and the other is a condition at infinity. Here I haven't imposed boundary condition yet. Okay, you remember that. I just guessed the theta dependence in this way, but I haven't solved I haven't imposed boundary condition yet. And by imposing boundary conditions, I can find the A and B. Let's impose boundary condition at infinity. The boundary condition at infinity says, when I take a gradient of phi has to be 0. So from the boundary condition at infinity, I can say something about A. Okay, but before we talk about that, let me give you the expression for velocity in polar coordinates. So since we are using polar coordinates, there are two velocity components. One is the radial velocity, which can be found by taking our derivative, and the other is the azimuthal velocity, which can be found by taking theta derivative and then divided by r. Okay, those are the expressions. So this is radial velocity, and this is the azimuthal velocity. So, for example, if I take r derivative, radial velocity, here I end up with A minus B over r squared cosine theta, right? So boundary condition at infinity, meaning that as r goes to infinity, the velocity has to vanish. As I said, if I'm far away from circular cylinder, all I'm going to see is a uniform flow. So any disturbance due to the circular cylinder has to vanish. So as R goes to infinity, this guy has to goes to 0 as R goes to infinity, meaning that what? As R goes to infinity, this guy goes away. I have A cosine theta. So meaning that has to be 0, which means capital A has to be 0. So this condition at infinity, A is equal to 0. Likewise, if you take a theta derivative, which is 1 over R d phi d theta, and then you end up with A plus B over R squared. I'm taking theta derivative, which is minus sine theta. So this guy has to go to 0 as R goes to infinity. Once again, I end up with A equal to 0. Okay? So both velocities vanish at infinity as R goes to infinity. So we don't need this. A is 0. Do you see what this term, this times this represent? AR cosine theta. That's A solution, right? So this is a linear combination. AR cosine theta plus B over R sine theta. So I'm adding two solutions. The Laplace equation is linear. So this is a solution of Laplace equation. This is a solution of Laplace equation. What is this? Right? The velocity potential for uniform stream is U times X. Because when I take X derivative, I end up with U. X is R cosine theta. So I said this is a solution of Laplace equation, right? Now we see that. Okay? So here we already include in Laplace the uniform flow. We don't need this anymore. That's why we said A equal to 0. Because this is general solution. So we end up with only this guy. And we can impose boundary B from this boundary condition. So let's do that. So capital phi, which is minus U cosine, which is B divided by R cosine theta. And now we impose boundary condition from the body boundary condition, which is this guy. I'm going to put star there. So star. We take the R derivative, and then I have B divided by R squared cosine theta. And then I have to evaluate at this guy at R equal to A to impose boundary condition. And then I end up with minus B A squared cosine theta. This has to be the same as the minus U cosine theta. Now we can drop this. I hope you can see why we pick cosine theta here. Okay? So we put capital phi is function of R and times cosine theta, right? And from the body boundary condition. So we can drop theta dependence like this, and then B is nothing but U a squared. So we finally determine two constants, unknown constants, a and b. So let me write whole total solution, which is a solution for uniform stream plus capital phi, and this is u r cosine theta, and this part is plus u a squared divided by r cosine theta. So this is a solution for a flow around the circular cylinder. Okay? So once you know the speed of stream and the radius, then you can write the solution here. U and A are the only two parameters in this problem. The speed of uniform flow and the radius of circular cylinder. Then this is a solution. And now, as I said, once you solve Laplace equation, then you can find the velocity vector, which is u r and u theta in this time, using here. So u r is once again, let me write down. So total velocity can be in this way. Okay. So now you can find a velocity field, velocity vector everywhere you want. Okay, anywhere, also including the surface, because you know the expression. You might, or you might not, worry about the 1 over r, because r equal to 0. This guy is infinite, which cannot be physical. But don't worry about it, because r, this is only true for r greater than a, right? Because these are the velocity field outside of circular cylinder. You can still find u r and u theta inside, although that has no physical meaning. Okay, this has a physical meaning only outside of circular cylinder. Although there is some solution inside, but we don't care. Okay? As long as any fluid particles inside doesn't come out through the surface, which we know that is true because we impose zero normal velocity condition. We can check easily. Let's check. So this guy has to be, this is total at r equal to a, has to be 0. Okay? That's our boundary condition. So should be true. But let's check. So the first one, d phi dr, is u cosine theta minus u a squared r squared cosine theta. And when I evaluate r equal to a, what happens? U cosine theta, a squared, that is 0. So whatever we have inside, we don't have to worry about the flow inside, which is an artificial thing because we are solving mathematically, and then nothing comes out because the normal velocity is 0. What happens to the tangential velocity then? I said, this is an inviscid flow, so we allow tangential velocity to be non-zero. So let's check. So this is a u theta, tangential velocity at r equal to a. So particularly we are interested in tangential velocity here. Okay. And then I have 1 over r, take the theta derivative minus u r sine theta, because first derivative of cosine theta is minus sine theta. And then I have u a squared divided by r, and again I have minus sine theta. True? And then evaluate r equal to a. And before you evaluate, you can see what we end up with minus u sine theta here, and I have 1 over r squared here, and evaluate a at r equal to a, then I end up with minus u sine theta. So tangential velocity at r equal to a on the surface of circular cylinder is minus 2u sine theta. Okay. So it doesn't have to be 0. Normal velocity has to be 0 everywhere. Tangential velocity is this, and doesn't have to be 0. So what happens? So flow is coming. Theta measures from here. So this is theta. So this is theta equal to 0, and this point is theta equal to pi. Then u theta is 0, and u theta equal to 0. Because, sine 0 is 0, sine pi equal to 0. So those are the stagnation points. Okay, that's what we call. Because, the fluid velocity equal to 0. Because the normal velocity is 0 everywhere. On those two particular points, not only normal velocity, but also the tangential velocity are equal to 0. So what happens here? So u theta here is theta equal to pi over 2. So what happens? This is a 1. U theta is equal to minus 2u. Does it make sense? Looks like a minus. Flow is coming from minus infinity to plus infinity. So flow has to be this way, positive direction, but I have a negative sign here. Why is that? So this doesn't make sense, right? Flow has to go around, cannot go that way, has to go this way, but I have minus sign. So did I solve wrong? The reason why I have minus sign is, u theta, we increase in a theta direction in this way. So u theta is positive direction is this way for u theta. So I have a minus sign. That's why I have a flow. Flow goes this way. Okay. So everything makes sense. And also here, theta is 3 pi over 2, which is minus 1, so u theta is 2u. And this time, theta increases this direction, so flow going this way. So let me put the direction of flow. So what happens is flow is coming in, and then split, and then it reaches 2u, and then becomes 0 again. So fluid particles goes from here to here. Velocity changes from 0 to 2u. So velocity increases from 0 to some value. So fluid particle has to accelerate. Otherwise, velocity cannot be changed. So this part, fluid particles accelerate. So you have acceleration here. On the other hand, real phase of the circular cylinder, fluid velocity goes from finite value to 0, so it has to be decelerated. So there is a deceleration. Okay. So fluid particle has to accelerate. So it has to catch up, run faster to get the value. And then here, once the fluid particle reaches on the top, then fluid particle can relax and decelerate and goes back to 0. So from Newton's law, which we use to write the momentum equation, when fluid accelerates, or when the fluid particle has the momentum, for momentum to change, the external force has to be applied, right? So that's what we did. So linear momentum is equal to force applied, right? That's basically the Newton's second law. So this is m times v, and when you take the time derivative, it's m times acceleration, right? Mass times acceleration is equal to applied force. So here, the momentum of fluid particle has been changed. So for that momentum to increase, the force has to be applied. What kind of force do we have? At this time, we didn't include gravity. And this time, we don't have viscosity, so there is no viscous stress. The only thing that makes the fluid particles to accelerate is pressure. Okay, so pressure does work to make fluid particles accelerate or decelerate. So when we compute the pressure by using Bernoulli equation, then we'll see how pressure acts to make fluid particles accelerate or decelerate. Okay, but to see exactly what's happening, we have to compute the pressure by using Bernoulli equation. Okay, so that's what we are going to do on next week, and then I'll talk about the flow a little bit more. Is there anything that I want to say today? I don't think that's it. Okay. Any question? There are only finite number of geometries for which you can solve Laplace equation analytically like this. Okay. Only a small number of geometries, you can solve analytically, the Laplace equation analytically. If you have a very complicated geometry, then you have to solve Laplace equation numerically. Okay, we'll talk about that later. But first, we will look at the simple geometry for which we can solve the Laplace equation analytically. Okay, that's what we will do. So we'll compute pressure, and then we'll integrate pressure to compute force on next Tuesday. All right.